Hey everybody, I'm going to do an abridged version, so only parts of chapter 6 and then followed by parts of chapter 7. But we're going to be talking about discrete and continuous probability distributions. So this first chapter, chapter 6, is about discrete probability distributions. And there's two types that we're going to talk about in the slides, but not necessarily in this video. So there are the Poisson distribution and the binomial distribution. The Poisson distribution has to do with a count model. So the number of occurrences of some event within some time span or some other interval, whether it might be spatial, something like that. And then binomial is given a set number of experiments, what's the probability that some fraction of them occur as a success or something like that. A really good example of a binomial distribution would be something like batting averages. If a baseball player gets up to bat, they get up to bat 4 times in a game. What's the probability that they get 3 hits? Something like this. Would be a binomial distribution. But you can check that out on the slides. But for now, I'm only going to talk about more general discrete probability distributions. So first, to define a probability distribution, it's going to be a listing of all the outcomes of an experiment and the associated probability. So like I was saying, if you're talking about a batter getting up to the plate, let's say they bat, they get a hit 30% of the time, you would have an outcome of 0, meaning no hit, 70% of the time. And then a hit, yes, that would be a 1, 30% of the time. Now this is there's only an outcome of 2 things, right? Only 2 things can occur, either a hit or not a hit. But you can also think of something like the batter can walk or something like this, right? So there are more outcomes and you can divide up the probabilities that way. But if you're just talking about whether or not you get a hit, it would be 30% for a hit, that would equal 1, and then 70% of not getting a hit. So there are a couple of characteristics to be wary about. The first is that the probability of a particular outcome has to be between 0 and 1 inclusive. So something has to happen, any given event has to have some probability. So for example, if we're talking about a batter, the probability of them getting a hit is going to have some probability between 0 and 1, right? So I said 30%, that would be 0.3. Maybe the probability that they walk is, 10%, so 0.1, but the probability of them hitting the baseball so hard that like the world ends or something like that, that can be an outcome, but that outcome is going to have probability 0. So any sort of outcome is going to have any probability between 0 and 1. Second is the outcomes are mutually exclusive. So you can't have a batter getting a hit and a walk at the same time. It has to be one or the other. And then kind of by extension, the list of the outcomes is exhaustive, such that the sum of the probabilities has to equal 1. And as I kind of mistakenly said before, something has to happen. An event has to occur. If you do this experiment, an outcome has to be realized. So there's going to be a probability equal to 1. So back to the trivial example of getting a hit or not getting a hit, and then the world ending because the ball was hit so hard, right? You have probability getting hit 30%, probability of not getting hit of 70%, and the probability of the world ending being 0, right? So the sum of these probabilities is going to equal 1. So here's a little example of a probability distribution. Let's pretend I flip a coin 3 times. In this case, I can flip a coin the first time and get tails, right? So that would be defined in this first column. If I get tails, it would be maybe here. If the second one is also tails, it'd be here. And the third one is also tails, we'd be here. This would be the number of heads would be 0. Now, there's multiple ways I can get the number of heads in sum to be 1, number of different ways I can get it to be 2, and number of different ways I can get it to be 3. So this is the all possible outcomes, right? The first one can have 1 or 2, be a head or a tail. So we have all tails here, all heads here. Then from the first tail, I can have, again, a tail or a head. And then here, after the second one's also a tail, I can have a tail or a head, right? So there's 8 possible outcomes. You could think of this as almost like those tree diagrams we talked about before. But this is an example of a probability distribution, or at least the beginning steps, right? So you write down all possible outcomes and write down the number of heads that you're interested in. And then we can actually write it as a probability distribution table. So here we have the number of heads, right? So if we flip 3 coins, the number of heads can be 0, it can be 1, it can be 2, or it can be 3. The probability of getting 3 heads if I flip 3 coins is going to be 1 out of 8 possible outcomes for a probability of about 12.5%. Similarly, the probability of getting 0 heads is 1 over 8 because it would be tails, 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 also 12.5%. And then probability of getting 1 or the probability of getting 2 is both going to be 37.5%. And then here you can kind of draw out the probability distribution in a graph form like this. So in any experiment of chance, the outcomes occur randomly and are so-called random variables. And the definition here, I'm just going to read off the slide, is a quantity resulting from an experiment that by chance can assume different values. So for example, a random variable is whether or not the batter gets a hit, whether or not, or the number of heads you get if you flip 3 coins. These are all examples of random variables. Some other examples listed here on the slides are the number of employees absent from the day shift on Monday, right? This could be any given number. The grade level of members at St. James High School varsity girls basketball. So grade level, even though it's not numeric, is still a random variable. The observation of their grade level is still a random thing, right? If I randomly select a girl on the basketball team, they can be of any grade level. So there's 2 types of random variables, just like kind of how I mentioned in the beginning. And there's going to be discrete probability distributions and continuous probability distributions. The first one we're going to talk about here is a discrete random variable. So a discrete random variable is a random variable that has values that are unique. So, or not unique, but separated. So for example, age would not be a discrete variable. Now you can talk about age as in somebody is 21, somebody is 22, somebody is 23. These have gaps, right? But in theory, you could be 22 and a half years old. However, the number of siblings you have, you can't really have like 2.39 siblings. It doesn't really make sense. So the number of siblings you have is going to be a discrete random variable, whereas how old you are or how long it takes you to walk to school is going to be a continuous random variable. So the definition of, so the way I always think of it is, can I further divide this by 2? If I can divide age by 2, if I'm 22 years old, I can divide age by 2, I'll get 11, kind of divide that by 2, and it still kind of makes sense, right? You're at some point, you're going to keep dividing by 2 and you're going to get a really fine decimal, but it still kind of makes sense because you can break down time from years to months to days to hours to minutes to seconds. For siblings, if I have 4 siblings, I can divide by 2. I'll get 2 siblings, divided by 2 again, I get 1 sibling, divide again, I get half a sibling. Now there are issues with the English language by having a half sibling, but realistically, that person is still a whole person. So you can't really have a quarter of a sibling or an eighth of a sibling. It doesn't really make sense. So the way to tell between discrete and continuous, again, is just by kind of, can you further divide and still have it make sense? So again, continuous random variables, we'll talk about this a little next time. But essentially, this is just can assume an infinite number of values within a given range because we're talking about continuity. So of course, some things that we're interested in when we have distributions is we want to know, can we find the average or the mean? And can we find the measure of dispersion or the variance? So with a just arbitrary, discrete, random, a probability distribution, both of these things are possible. So the way we're going to do this is really similar to a weighted average, where we take our x values here and we multiply them by the probability that each one occurs. So remember, the probability is going to be between 0 and 1. So this is always going to be a decimal number. And then X can be whatever value it is, right? So if I'm flipping coins again, and I say, the probability of me getting 0 heads, 1 head, 2 heads, or 3 heads is going to follow this probability distribution. The average number of heads is not necessarily taking the average of 0, 1, 2, and 3, but rather is taking the weighted average of 0 weighted by 1/8 probability, 1 weighted by 3/8 probability, and so on. So you have to keep multiplying the value by the probability, and that will give you the average of the distribution. Now, why is this? If we kind of go back a few slides, we can see that if we take the average, it's actually going to be right in the middle anyway, because it's symmetric. However, if this one was just much more likely to occur, you would want that reflected in the mean. You would want things that are much more likely to have a higher weight in the mean. So that's why we do it that way. Similarly, variance is going to be calculated almost exactly the same way. We're still going to take deviations from the mean, so X minus mu. We still want to figure that out. But again, we can't just use X minus mu, because if we average these out, we're going to get 0. So we need to make them all positive. We do this by squaring. So we'll have X minus mu squared. And then again, we're going to have squared deviations from the mean, but we don't want to just take the average squared deviation from the mean. We want to weight it by the probability of observing this deviation from the mean. So what we're going to do is we're going to calculate each squared deviation, multiply it by the probability. So for example, we'll calculate some average for the number of heads. I think it's going to be about 1.5. And we're going to subtract that from each X value. So subtract that from 0, subtract that from 1, subtract that from 2, subtract that from 3, square each of these values and multiply it by the respective probabilities. So here's an example of some car dealership and the number of cars they sold and the probability of selling that number of cars. We've got the probability distributions here. So for the average, we're going to do 0 times 0.1. This is obviously going to equal 0. 1 times 0.2, it's going to be 0.2. 2 times 0.3 is 0.6. 3 times 0.3 is 0.9. 4 times 0.1 is 0.4. And if we add these all up, like the formula says, we're going to get our mu. So it's relatively simple if you have the values and the associated probabilities with each one to find that average. Similarly, you can also find the variance this way as well. I'm not going to go through the math on this one. I'll let you guys kind of take a look at it and think through it. But I'm going to stop the video here and move on to the next chapter.